language. We're going to be looking now, you guys, can you take out that sheet that we talked about last class where it talked about independent samples versus matched or dependent samples? You know what I'm talking about? Go ahead and take that out. And I'd like to look at that and make sure, and if you don't have that, I do have a couple. I think it says independent samples versus paired samples. And I believe there were 8 examples that we went through and looked at. I'd like to just make sure that we looked at all those scenarios before we jump into Chapter 10 and make sure that we have kind of a good understanding about what it means to be matched versus what it means to be completely independent. All right, so let's look at these and just kind of get an idea of what we think each of these answers are. So let's look at problem number 1. And we're just trying to decide if they are dependent or independent samples. So what do you think about problem number 1? Those are independent. We've got 2 totally different situations. They're not matched in any way. They're 2 tire brands. And they're on 2 different sets of cars even. Wouldn't you agree? So that is independent samples. So we want to make sure that we're keeping track of that. It looks like my pen's going to die. Awesome sauce. What do you think about B? Huh? That's paired. So and it's paired by what? Keverlyn, I'm going to need you to keep your eyes open, baby doll. What do you think about B? It's paired because it's matched by car, right? So this is a paired sample. Very good. How about number? So that's an example of a situation where an experiment where you can either match it or not match it. What about problem number 2? What do you think about this one? What's it paired by? The actual workers, right? So this is paired as well. Good. How about number 3? Those are independent, 2 totally different samples, right? And you're just comparing the 2 samples. They're not matched in any way. How about number 4? That's also paired. What's it paired by? The actual person, right? The woman itself. Good. It's like that's sometimes called the before and after design because you're measuring them before a treatment and then measuring them after a treatment. So anytime you have a before and after, that is a paired sample. Good. How about number 5? Okay. So we have 9 pairs of pigs. The pigs in each pair. What do you think? Even though it says the word pair, it's still independent, right? So don't let that freak you out. Good. All right, and then number 6. So let's look at A first. So we have 100 plots with one fertilizer and 100 plots with a different fertilizer. That's going to be independent, totally. And then when we look at 6B, that one's the paired situation because you're taking one plot and dividing it into 2. So it's paired by plot. Why might that be important? If you look at 6B, why might taking a plot of land and pairing it be a better design than, let's say, 6A? What do you think, Keverlyn? So the location of the plot's going to matter because you have sun, you have different environmental factors, right, that would affect the fertilizer treatment. Good. So we want to kind of block by plot. That sounds weird to say. All right, what do you think about number 7? So we have college teachers, and we're comparing them, male and female. Those are definitely not paired in any way, 2 totally different, so we have independent samples. And then what do you think about number 8? That one is paired. What's it paired by? The people actually performing the it's really bad. The people actually performing the calculations. That is so bloody. Come on, King. Recalibrate. It's not happy. Anyway, the people performing the calculations themselves, right? So you're the speed of the fingers of the person on the calculator, so to speak. All right, excellent. So it's important as we move forward that we understand the difference between a paired sample and independent samples And all of these, by the way, that we just talked about, the paired versus independent, deal with means, okay? So we have a matched pair t-test or just a regular t-test. We are eventually going to do something called a two sample test, and those are for independent samples. Remember, t's and means go together. But we're going to kind of follow the way of the book, and the book comes back to proportions again. So we're going to leave the idea of a t-test, and we're going to come back to what do we use for proportions? Z's, right? So we're going to come back to that idea. Now, two proportions is a special case, okay? And we're going to talk something about pooling, speaking of lifeguarding and pooling. Kind of different idea, but we're going to talk about what that means and how that applies to this particular scenario. There are some conditions we're going to have to look at. We're going to look at confidence intervals. We're going to look at a significance test, and we're going to look at just this one type of test with two different proportions. Okay? So I want us to kind of read this example or read this idea, and I want to think about what this looks like and why these might be independent samples. So take a second. I'm going to turn the lights out so it's a little easier on your eye. So let's make sure we just kind of revisit the idea of notation, okay? So we have two different either populations or treatments depending on whether we're doing an experiment or the effectiveness, etc. The parameter, we're going to use notations as just your regular P, but we're going to have to denote notationally with subscripts. So we have population 1 versus population 2, which is why we're using 1s and 2s. Sometimes you do A's and B's. Oftentimes, we'll use a subscript that denotes a characteristic about that population, like males and females, so we would use M and F. So those subscripts that you're using are going to be reflective of their separate populations, okay? The statistic is, and for proportions is P hat, and your sample sizes, again, they just carry through that same notation, that's all, okay? No big deal. All right. Again, lots of words here, but let's talk a little bit about the conditions. And we know that with a one sample proportion, right, a one proportion z-test, that we have these different characteristics that we have to check for, conditions, so to speak, right? We have to check the normal condition. And remember, for proportions, it's NP is greater than 10 and n1 times 1 minus p is greater than 10. We have the center, or the mean, is just the proportion, and we have the spread is basically going to be the independent condition. We want no more than 10% of the population, right? So let's look at this scenario, okay? So if we're looking at the difference, notice, difference between two proportions, okay? That's what we're looking at now. Two different independent samples, and we're looking at the difference between them. We'll start with a known success of each, okay? So let's say we have two schools. Homework seems to be a big thing that people aren't really wanting to do a whole lot of, so let's compare ourselves to these two schools. So school 1, we have 70% of the students, and school 2, 50, okay? What can we say about the difference between those two sample proportions? And notice the notation. What can we say about this? Let's look at the situation. We have school 1, school 2. What is P hat 1? Looking at the information given to you. Okay, so, nope, not 0.7. 0.7 is the regular P, isn't it? Isn't that just the parameter that's stated? So we look, this information tells us P hat. Do you agree? Okay, so kind of like the beginning there, that's the claim, so to speak. That's the parameter, okay? So what we're going to write P hat as a fraction or a ratio. So what out of what? We don't know, right? Would you agree? So we would say x over 100. Would you agree? And P hat 2, we would say x over 200. Different sample sizes. How is that going to affect us? Well, that comes into play in a little bit, okay? Let's keep talking. All right? So, if we look at two proportions, and Fathom is a computer program. I actually learned more about it this weekend. Don't worry too much about it. For your purposes, it's like a jump. Remember how we used jump at the beginning of the year? It's a little bit like that, but a heck of a lot more powerful. They can create some of these interesting computer printouts. But let's just look at some of these graphs. Let me try to make it a little bit bigger so we can kind of see it a little bit better maybe. So if we look at these, okay, let's just look at the graphs, okay? So we have p hat 1. I'm going to make this a little, so this is just our sample proportion from the first. Here's our sample proportion from the second, and here's the difference. Do you notice anything? Let's comment on this, their centers. What do you notice about their centers? The center here is at 0.7. Would you agree? And wasn't that the claim anyway? 0.7? All right. How about p hat 2? Centered at 0.5. Okay. And what do you notice about the difference? The difference, where is it centered? Hard to see, but it's at 0.2. Does that kind of make sense? Right? 0.7 minus 0.5. Okay, perfect. And then what do you notice about their spreads? Let's comment on that. Just looking at the picture. Well, that's shape, so they're all relatively normal. That's good. So if you have a normal distribution and you subtract a normal distribution, you're going to get a normal distribution. Great, okay. What about the spread? Comment on size. Small, big, relatively the same. What do you think? This one goes from 0.55 to 0.85, right? So it's hard to see, but they're saying the spread is 0.046. This spread is thank you, I can't read that. And then this one is 0.058. So what do you think? Right? What we want to do is we want to estimate the we call the standard error. Okay? We want to estimate that the best we can. And to do that, we have to do something called pool our data. Okay? So for those of you that might have looked on and read on, this is why we have to do it. We want to estimate our standard error the best way we can. So we're actually going to take whatever our x values are, kind of like if we go back over here, we're going to take, so in other words, we are going to take these values and we're going to pool them. So we're going to have over 300 and then whatever these x's are and add them. Okay, we're going to make one statistic. Does that make sense? Okay, so we'll look at that in just a second. Good. Maybe. Oh, goodness, I'm trying to delete things. No, don't want to delete anything. Thank you. Come on. Here we go, Monday. All right. So here are the formulas. And I'd like for you to do me a favor and take your formula sheet out for me for just a second and see if these pooled formulas, these formulas for two independent samples are on your formula sheet, or at least where they are on your formula sheet. So you want to be looking on the right-hand column, okay? And we want to be looking at difference of sampling proportions. So you look at it on the, I think it's on the bottom right side of your sheet. Does that look right? Now it's going to look a little bit different than what you see up here, okay? Does it look exactly the same? Yeah. Okay, good. So it looks exactly the same. There is one that's a standard error where it's like, looks a little different. I think it's the one underneath it. That's okay. But basically the standard deviation is just the square root of, now what did we do before? The regular one was just kind of like the first, right? We didn't have to worry too much about from two different samples. Do you agree? So here, when you have two samples, you're going to add the standard deviations of both. Is that okay? Formula's there. Don't have to memorize it. It's there. Done. Good? All right. Perfect. Keep forgetting I can do that. All right. So this is just a bigger picture. There's your formula. The mean is just the subtraction, which we get, right? So that's good. The mean is what we expect it to be. The standard deviation is the sum of the two. Always the sum. Don't we always add standard deviations anyway? Remember that from a while ago? Always add them. Good. All right, so let's try an example. okay? Let's actually try this one, see how we do. I know we're tired, it's Monday, I get it, but let's look at it, okay? So we have our two high schools, okay? And we have a large population. Let me make this a little bit bigger, like I said, so we can see it good. And let's see if we can answer the question, okay? So, read through it. I'm going to pause the recording for a second, and let's kind of come up with what we think our null and alternative hypotheses, or what are our parameter. Let's do our state section of the information, okay? So if you read this problem, it's already gone ahead and given you what the difference of the two proportions are. Do you agree? The two sample proportions, it's told us we don't know how many out of 100 and how many out of 200, but I know that they report together that the difference between the sample proportions is 10%. Are we good so far? Okay. Good. So let's describe the shape, center, and spread of what this might look like. So we can tell you can know right away that the shape should be what? The shape should be normal, because if you start with a normal distribution and you subtract another normal distribution, you're going to get a normal distribution. Would you agree? So we know that the shape is normal. Oops. But in order to check that, because were we told earlier that they were normal to begin with? So what do we need to check? What's the normal condition for proportions? So let's check that. Do you mind? Go ahead and do that. Before I show you, I want you to check the n times p, and you're going to have to do it for each sample independently. I don't want to use the word independent because they're different things, but sample 1 and sample 2. You got to check it for both of them. So you're checking 4 things. Does that make sense? Okay. So go ahead and try that. I'll leave those numbers up there for you so you can check it. Let's see how we did. So we know that looking at the sample size of the first population was 100, right? So 100, and it was 70% of those 100 people did homework. So we have 70, and then if we do times 1 minus p, we have 30. Both are greater than 10. Do you agree? So sample 1 works. What about population 1 works. What about population 2? Well, we have 50% of 200, and that's also greater than 10. Would you agree? So they're all at least 10. Therefore, the sampling distribution of the difference of the sample proportions is also normal. Okay? But you have to check for both. Are we okay with that? When you have 2 independent samples. Okay, good. What about, so we got shape. What about center? Did they give it to us? What was the center? 0.2, right? That wasn't the sample though, was it? The sample was 0.1, wasn't it? Didn't they tell you that in the problem that the sample was 0.1? All right, that's our sample. The claim is 0.7 minus 0.5. Do you agree? Okay, good. So we know that that's our center. And then how about the spread? Okay, let's think about what that's going to look like. The spread, we have to look at the formula for the standard deviation. So let's make sure that the formula makes sense. So we're looking at using the formula on our formula sheet. We have P for both sample 1 and sample 2. The sample sizes for each of those. It's a matter of just plugging it in. Are we okay so far? Any questions so far? All right. Good. So we have our shape, our center, and our spread. Good? We could write it like this. Would you agree? Okay, because it's normal. And we have our center and we have our spread. And that's of our population. That's of everybody, both samples, or both populations. Good. All right. So let's find the probability of getting a difference in the sample proportions of 10 or less from the 2 surveys. What are we finding here? How likely is it that our sample happened? That should sound familiar to you as something that we found before. Right? So let's keep looking and let's see what it would be. So what are we looking at? Well, we're going to standardize and find our, what's another word for this value? Test statistic, right? It's a z-value, would you agree? And we went ahead and subtracted what? Well, where does the 0.1 come from? That's our statistic. What's the 0.2? The parameter. And then what is the 0.058? Okay? We just happened to find those independently before we got to this part. Are we okay so far? Yeah? New formulas though, right? But the general formula for the test statistic is the same every time. It's just that now we have a new standard deviation formula to use. That's really the only, and we had to subtract to get each of those numbers. That's it. We can make it look really complicated, and I have a feeling they're going to do that for the big overall formula, but it's sometimes better to do them individually. All right? We're not going to use the table because that's goofy. So let's go ahead and find the probability, okay? The book is old. It wants to use tables, and we have calculators and technology now. So let's do that. So we're going to use normal CDF. It's our favorite function on the calculator. I feel like we do it at least once a day, right? What's the probability that our sample happened? Tell me what I'm typing in. Notice how it's shaded, so our alternative hypothesis would be less than, right? In other words, do we think that school 2 does less homework than school 1? Isn't that really what we're testing? Right? If we're going to use these, we okay so far? Tell me what you get. Because your number's going to be a little bit off of this one. Exactly 0.0427? Oh, cool. Okay. Yeah, the tables sometimes are off by a little bit. Your calculators are much, much more exact. But I'm glad to see that they're pretty close. That's good. All right, so what is that again, Justin? You told me earlier? It's a p-value, right? Which is, what is a p-value? It's the likelihood or the probability of us getting our sample as extreme or up to as extreme as our sample that we got, which is describing the shading of our curve, right? How likely is it that that happened? Well, not real likely. Would you agree? What are we comparing that to? Not a p-value. Our alpha, which if it's not stated is usually 0.05. So what kind of conclusion can we make just in general terms about school 1 and school 2? Okay, so I'm going to stop Mason right there. He stated we have significant evidence. Beautiful. When I was grading some of your tests, and we'll talk more about this during Flex, we either have evidence or we don't have evidence. So this is the only time where we have evidence is if our p-value is small enough. If our p-value is large, we got nothing. We don't have evidence to say anything. Some of you were trying to say we have evidence to say that the null is true. What? You can't do that. Okay? So we don't have evidence to say anything if our p-value is too high. Thank you, Mason, for starting off so wonderfully. So finish what you were saying, sweetheart. Well, we have evidence. The p-value is what it is. So what's our evidence saying? Be specific about school 1 and school 2. What were we trying to say in the beginning? What was our, let's go back and write our null alternative. What would our null be? P1 would equal P2? Would you agree that their proportions are the same? They each do the same amount of homework? What about the alternative? What did we think happened with the school 2? So we can either do this, or we can do what Mike just said. P1 minus P2 is greater than 0. Would you agree? Either one are okay. You can also come up here and say P1 minus P2 equals 0. Perfect. Okay? So let's go back to our conclusion again. We have evidence to suggest that who does more homework? School 1 does more homework. 70% versus 50%. Right? Even though their population sizes were different. Not necessarily. but it probably has something to do with it. Would you agree? Okay. How do we feel so far? Yeah? Lol. I mean, it's not really anything different, is it? It's just new formulas. Okay? And a couple other things we have to test for with our conditions. Not too bad. All right. So, based on what we said our conclusion was, does our result give us reason to doubt the counselor's reported value of 20%? No, 10%, sorry. Yeah, we have evidence to suggest doubt, don't we? There's only a 4% chance, remember this is p-value, of getting a difference in sample proportions as small or smaller than what we have. Okay, that's really a nice interpretation of p-value. How likely is it that our sample was as extreme or more extreme than what needed to be? Okay? Y'all seem a little tired today. It does seem suspicious. Perfect. All right. Let's talk about confidence intervals. And again, let's just look at what's in blue. And let's break it down. Okay? What is that information? And remember, with confidence intervals, we're always using what? P hat. I feel like we should all wear hats when we do confidence intervals, right? We're going to make hats. Always using P hats. Only P hats here. Would you agree? Okay. So with confidence intervals, what is that first part? Look at your formula sheet. What does the formula sheet say? It doesn't give, it just gives you a general word description. So what is that? That's the statistic. This is our Z star critical value. And it's Z because, I can't spell critical, because it's proportions, right? Normal. And then what is all this garbage? It's not garbage. Standard, it's called the standard error because we're using p hats, not p's. When you use regular p's, it's called the standard deviation, but that's fine. So it's our standard error. Yeah? Isn't that the same thing we're always doing every time anyway? Good. Beautiful. Same thing. The only thing that, by the way, remember on your test, well, it's on your test, but it's fine. Here, isn't this the only condition you have to recheck if you're doing both? The normal condition? Because what's different about the normal condition for intervals, confidence intervals, than it is for tests?